several weeks ago we started doing heaps.
And in the assignment I have posted, you will see many applications of heap. Okay, we won't see all the applications in the class, but what was useful in the applications we saw in the class was this idea of storing a tree in an array. Instead of pointers, you store in an array, and then within the array you can traverse the tree. You can go to the parent, you can go to left or right child. So that was the augmented tree data structure application, which is solving multi-increment problem, right? So this is called interval tree, or in the literature it's also mainly called segment tree. Okay, so we did this, the tree that stores the intervals. This is called the segment tree, and so in the internal nodes we can augment them. We can store this information of, for example, what increment happened. So we can store it in the blue, and whenever a multi-increment happens, you don't have to scan linearly.
Everything, you can just go in log n steps to the internal node and there put a single increment. And then reporting was easy, right? So this was log n everything, and similarly we solved this dynamic range bin where you want to report the minimum in a subsequence from I to j, and dynamic because you can update the values. ith one you can set to a whenever you want. So here again the augmentation will be in the internal nodes. The red nodes will store the min of that particular interval, and you can decompose any I comma j segment or subsequence into these basic intervals, and then you can do again a tree search, right? So these problems we have solved in log n. Any questions till now? So more applications of heap and these kind of data structures augmented are available in the assignment. So what we will do next is another way to store a tree with a new application. So we have seen many ways to store a tree data structure. So which we can say type of data storage of a tree. So first is when we saw a binary search tree, red black tree and so on, so there we had pointers, pointer to the root and then pointer to the children. Okay, so we store pointer to the root because it is unique, and then from there we can traverse the tree top to bottom. So this example is mainly our red black tree that we did in detail. Second is this heap style, where we store the tree in an array, and then there are no pointers. We just have formulas to go to the parent or to go to the parent of ith location or children of ith location. Right? We use the formulas. So that is possible because of the complete binary tree assumption. so we can store it in an array. Right, so that idea gave us heaps. So, so the new type that we will see, I mean, at some point you will see, is we'll still use an array, and we will have a tree structure in mind, but it will be very different from a heap. So what we will do now is we'll use an array to store the parents of the ith location. Okay, so where the parent of ith location lives. So we'll use an array A such that E of I will store the parent of I. So this parent is in the tree. Okay, so there is some abstract tree data structure like you had in the heap, but the way it will be stored in the array is very different from a heap. So here, when you go to the ith location, what you will see written there is the parent of I. Okay, so you can so it's kind of one directional compared to heap. So in the heap, you can go to both parent and children of I. But now in the array, since you only have the parent, you can only go to the parent. Okay, so this here, I mean, if you want to find the children, that will be a harder problem. I mean, you have to scan the array a lot. But parent is easy to find. That is stored in AI, in the array A at location I. So that is the new type we will do. So let us do this example. So now it is better to draw reverse arrows. So this reverse arrow shows that the parent of 0 is 5 and parent of 1 is also 5. Okay, instead of the child, we are now drawing the arrow towards the parent. So this is the abstract tree, and the array A will look like this. So the locations are 0, 1, 2, 3, 4, 5. And what will be the entries? So what is A0? A0 has to be the parent of 0, right? So that is 5. And same as A1 also has the same parent. What is A2? Yeah, so 2, 3, 4 are 0. And what is A5? 5 is the root. So in the array, we somehow want to highlight that this is a root. Right? So what we can do is we can just add a self loop. We can just say that E5 is 5. Okay, so from the array it is clear there is a unique location whose parent is itself, so that is the root. So you know the root looking at the array, and basically the root is the fixed point in the array. Right? So fixed point there is unique. So 5 is the root, and then from there you can read the array and you can build the tree. So it goes both ways. Okay, so this is a completely new way of storing a tree data structure. Okay, in without any loss or extra information. So this signifies the root. Any questions? So now we'll spend 1 or 2 classes on this data structure, because this solves a difficult problem. It's a practical problem. It is called set operations. Okay. How come? No. This is just an example. The 0th. I mean, I could just swap 0 and 1, 0 and 4 in the tree. Then everything changes. These are just numbers, right? So 0 can appear much below. So parent of 0 will be anything. A0 is an arbitrary value. So this will be used to define the set data structure, which will afford operations of union and find. Okay, so this is the set union find data structure. So this third type we will use to design a set data structure, which does the following. So it has so what are the initial sets? The initial sets are singleton sets. Okay, set 0, set 1, dot set n minus 1. This is how this data structure starts. Okay, n sets, each of size 1, taking and the universe is 0 to n minus 1. Okay, so this is the initialization. This basically is creation of the set data structure. And once the data structure is created, the sets are created, you can do now operations. So the first operation is same set. Or this is the function that your the mathematical model of set ds contains or affords. So same set I comma j will return yes or no. It will return yes if and only if I and j are in the same set. And it affords the operation of union. So what is union I comma j? This is there is a set containing I, there is a set containing j, you take the union. So the previous sets are deleted and the union is the single set replacing them. So maybe I should have said that this is disjoint union, disjoint set data structure. Sets are always disjoint. So you start with disjoint singletons and then you take union and you keep deleting the previous stuff. So that is what union will do. That contain I respectively j. Okay, so it can happen that I and j come from the same set. In that case, union will not do anything. But when they are coming from different sets, then it will take the union and delete the earlier ones. Is the modeling clear? So the way this is implemented is a bit complicated to analyze. Since this is a baby codes, we will only analyze a simple result. We will not do the real result here. So that you have to, if you are interested, you can do on your own. So what is the first thing that comes to your mind to solve this problem? Well, maybe I should state the problem. So the question here is, come up with a data structure such that everything works in log n. Okay, so as always, this is the mathematical modeling, the operations you want, and in terms of the size of the universe, you want everything to work in log n time, right? Which is exponentially fast compared to the sizes, because if you look at the set, the disjoint sets you have, they are many, they can be n many, and their sizes also can be around n. Right? So in terms of the things you are dealing with, the demand is very, very high. This is, you are asking for log n. So here we will use the type 3 version that we just introduced. So all the disjoint sets in your data structure will look like this orange picture. Okay, every set is like this. So this represents the set 0, 1, ... 5. And then there will be something like 6, 7, 8 and so on. Okay, so our sets will be stored like this. But you also know graphs from before. So you can also give a graph based construction. Well, at least you can analyze it. So if you were to store this in a graph, how will you do this? How will you store, how can you store these sets, say starting with the singleton sets in a graph? So what does a set represent in a graph, intuitively? So the elements, the elements 0 to n minus 1, they represent vertices. Sets, you may want them to represent connected components, right? So when you start, you can have connected components 0, 1, ... n minus 1, which means that there is no edge. Okay, that is what the initial graph is. What do you do when union I comma j is called? Then you can draw the edge I to j. Right? So if you draw edge I to j, then the whole connected component of I and the connected component of j, they become one connected component. So that is exactly union. Right? So there is a natural way to do this using graphs. So maintain these connected component array such that CC connected component I value is the label of the connected component. That contains I. Okay, so with the graph you can maintain a CC array, and then same set and union can be implemented like this. So union is or same set I comma j will output what? It will output yes if and only if CCI is equal to CCJ. And union will just add an extra edge, a new edge. To the set E, right? So this is a valid implementation of the disjoint set data structure using this interesting DS of graph, and you store the connected component labels for every vertex. What is the problem with this? Right, so that is one problem, that when you are adding the edge I comma j, you have to basically look at all the vertices which are now connected and give them a single label, the same connected component label, right? So which is bad both ways. If you do BFS, it is order n, plus the CC array update already is order n. So it is bad both ways, both time and number of places. So these operations take order n time. Let's say you use breadth first search for the CC update. It's not just order n, it's actually, so this is more than n, right? This is big omega n. So then necessarily in worst case, it will take linear time. It will not take less. So this doesn't help. I mean, it solves it is a valid data structure for disjoint set problem, but the time is still very high. It's far from log n. So that is the idea 0. So idea 1 will be using the new. So you need something new, and that is what we'll now discuss. So instead of graph, we'll use this tree of type 3. So for each set, maintain a rooted tree. In the form of type 3. Right, so type 3 was what we started with, this orange tree stored in this green array, where AI is basically parent of I. That's what your sets are. So which means something like this. So 2, 4, 6 set, and set 0 and set 5 and set 1, 3. Okay, so we have universes from 0 to 6, and the set DS has 4 sets. They are disjoint and they cover everything. So they have been formed naturally by taking union of 2, 4, 6 singletons, right? And the union of 1 and 3 singletons. So you are at this stage. So what is the answer of same set 0, 5? There is no, right? Because 0 and 5 are in different sets. But same set 2 comma 6, it is yes because they are in the same set. And when you take union of 2 comma 0, what happens? You get the set 0 comma 2 comma 4 comma 6, right? So, and how does it look in the tree structure of type 3? So it will look like this. I mean, this is one option. So 2, 4, 6, one option is this, that, I mean, it depends how you will do the union. But this is one possible option, that you store 2, 4, 6 at this point like this. So 2 is the root. So in the array you have, yeah, I don't know. So okay, so array is, let's say, A. So A4, when you go to that location 4, it will store 2. Okay, and A6 will also store 2, and A2 will also store 2. Okay, so that is how it is being stored, and what I'm drawing is just a schematic. Okay, so A0 stores 0, A5 stores 5, A1 stores 1, and A3 stores 1. Okay, so that is the full disjoint set DS in the array. Clear? So that is our almost final construction. This is how storage will happen, and now we have to see and analyze the time complexity of these operations. So let's just check union also. So union 4 comma 3 will do what? So 2, 4, 6 set and 1, 3 set have to be made one set. So which means that, what should we do? I mean, we can do many things, but I'll just give one example. So what you can do is, one valid example will be that you just make the parent of 1 4. So bring it here. Okay. So the set 1 comma 3 and then 2 comma 4 comma 6, that set is this. What we have done is that the root of this, of where 3 is, which is 1, it is no more a root. We make its parent something which lives in 2, 4, 6. Okay, so it becomes this bigger tree. In fact, what we have done is just parent of 3 we have set to 4. So it happens in constant time. In the array, you just have to make a little change. So that's what we have done. So we did, we first find the, actually no, it takes a bit longer. So root of 3 has to be found. So first you have to find the root of 3. So second element, argument of union is 3. So go to that, find its root. Well, here it was easy because the parent is already the root. But maybe if the tree was big, then you have to go all the way to the top, and there the root will be found. So it will take some time equal to the depth of that tree. So find this. So find root of 3, and then you set the parent of this root that you have found, parent of 1 to 4. Root of, yeah, so you have to find the root, which is what we have done. Yes, so that will be another find. So then you will take more time. You will take the time equal to depth of 3 and depth of 4. So that will be more time, right? So either you do find once or you do find twice, and then you just change the parent of one of the roots. So these are so there are many options. All of them have been explored, and we will see one of the better ones. So yeah, so let us just jump to the pseudocode then. So I finds the root. So what is that code? So find the root of the tree having I. So what it will do is, how do you find the root in a tree? Yeah, since all you have in the array is parent information, you just keep going to the parent, so it's a while loop till you reach itself. So that is the root. So if parent is itself, then you have found the root, so you return I. Else, what should you do? So the key code here is a recursive call, right? Yeah, so you will return find, you will call find on the parent. That's the key part. So this is the recursive, it's a recursive function. Goes to the parent and calls itself. So this is tailor-made to the array, the type 3 storage style. Next, let us do same set. So same set, whether I and J are in the same sets or same trees, whether the trees are the same. So what will you do here? Yeah, since we have implemented find, just call find. So if the roots of I and J are the same, then it's the same set. Else not. And finally the union. So what do you do in the union? At least for now the placeholder code is here in green. Right, for J find the root and then change its parent to I. So K is the parent of J, K is find J. So the root of J is found and call that K. And change its parent to I. Okay, so all three operations are implemented like this, and the data structure is also clear now. What remains is the time complexity. So is this really log n? Correct. So there is a skew tree problem. But before that, we write the time complexity as a function. So time is height of this height of the trees. We can be more specific. So time for find I height of this tree where I lives. Okay, so just check the code of find I. So what you are doing in find I is this simple-minded going to all these ancestors. So parent, grandparent, and so on, great grandparent. So that is the. I mean, in the worst case, if I was in the leaf, then in the worst case, you are traveling the height of that tree. Right? So whatever is the height of the root, that much time it will take. And find is being used in all the other operations, so this is what it takes. It cannot be faster than this. Which, as somebody said, in a bad example, this can be n. Right? Because we are not doing anything special to control the height. So height can very well become n or n minus 1. Because what you may have is this chain. Okay, you may have this chain where the sequence of unions were, I think, you take union of 0 and 1, then you take union of 1 and 2, and so on. So those sequence of unions will give you this tree. So it is the whole set, and at every point this find is requiring order n, theta n time. Right? So this is still not better than your graph solution. So what should be done? By a small change here you can make it log n. Do you know how? What is the small change? The root, you want to connect the two roots. Yes, that I think will also work. Yeah, so that is what is called path compression. That's a trick we'll not analyze. Let me do something even simpler, which is when we are doing the union, no, actually, I think your idea is right. We'll start with that. So in this case, what we should have done is, the way you should modify the union code is we should make parent of 1 equal to 2. Okay, instead of going down to 4, which is actually really at the leaf of the tree. So this is unnecessarily increasing the height. So to not increase the height, we should just hook 1 to 2. So that will minimize the height. So let's do that. So that is idea 2. So hook the root. Okay, so well that is what we'll do, but do you want to also qualify which tree will be added to what. Yeah, exactly. So you have to be careful about the size also. So the ideally what you, or intuitively what you want is the smaller tree should be moved to the larger one, the bigger one. So hook the root of the smaller tree to the root of the larger tree. So in the same example, when you were doing 2, 4, 6 and 1, 3, so the union of this, so second tree is the smaller tree. So we were right in attaching that to the bigger one. But what we did wrong there was just that we increased the height. So now we will not increase the height. Well, actually we will increase the height, but we'll try to minimize that. So we'll do this. No, actually this did not, this increased the height by +1. And previously also it was +1. Okay, so here you don't see the difference, but you can see that the connections have changed. What the advantage is we'll analyze, but the connection, instead of connecting 1 to 4, we are connecting 1 only to 2, which is just the root. Okay, so the root is attached to the root. That's point number 1. Point number 2 is that the smaller tree should be moved and the larger tree should not, should stay the same. Okay, it will just, the only change will be that in the larger tree, which here 2, 4, 6 are 3 elements, there the root now has an extra subtree. And this extra subtree has to be smaller. And I guess when the sizes are equal, then you can do anything. Okay, but when the sizes are different, focus on the smaller tree. No, so that's another thing. Smaller and larger tree means size, means the number of nodes, but you can also, I mean, in parallel or as an alternative, you can look at the height instead of the size. And then you can analyze as an exercise what happens. Hint is that that will also work. So this is by size. What about using the height? Okay, so I'm not doing that part because our proof will work with size already. So size just means number of nodes. But you can check the height ID also. Yeah. Yes, so we will maintain the size as an extra parameter or extra variable. In fact, we can do the pseudocode in this class. So let's do this fast union. So here we'll maintain the size array as suggested. So this will, since we need the sizes of the sets, we'll just put that in an additional array. And in the union it will change. So that's the new one, new implementation of union. So again you find the two roots. by find. Okay, so the roots are K and L of these two sets that you want to take union. And let's just assume that K and L are different. Otherwise, you don't have to do anything. So K and L, so these are different sets. Now you have to look at the sizes. So if the size of K, or K is the smaller tree, then what you want to do is this connection, right? You want to, so L is this, K is this, you want to connect it like this. K is the smaller one, so just change its parent to L. So let's do that in the code. And how will the size change? So size of K will become, actually let me not do that first, that will be a erroneous pseudocode. Let's first update the size of L, because that grows by the size of K. So this plus size of K, okay. So size of L is incremented. So now it's a bigger tree. And now what do you do with size of K? Well, now K is not a tree anymore. So this we can just assign 0, which means it's not a tree. K is not a standalone tree. Okay, only L is, and L size is grown. And the symmetric thing otherwise. So if size, if L is smaller, then you will write the symmetric code. So just flip L and K. So parent of L is K. Size of K is incremented by size of L. And after that you assign size of L to 0. Yeah, so that finishes else, and it also finishes the code. Is this clear? Yeah, so simple enough. Now the analysis part, I think our time is up. You have to analyze why this is actually fast. What is the improvement over the previous union code? So this we'll do next time. So what we will show is this lemma, that now the height of any tree here is less than equal to log n. Okay, so now the way we are doing union, no tree will have height more than log, which will combined with your time complexity, time for find I will become log n. Okay, so let's do that next time.